Chapter 10, Sinusoidal Steady-State Power Calculations. In this lecture, we will define instantaneous power, average power, which is also known as real power, and reactive power. We will introduce the equations associated with each concept and perform example problems demonstrating their relationships and how to calculate them in a circuit. We are looking at objective number 1, which is to understand AC power concepts, their relationships to one another, and how to calculate them in a circuit. We'll first discuss instantaneous power. The concept of instantaneous power is not new to us. We have been calculating instantaneous power since chapter 1. We just never called it instantaneous power. Instead, we simply called it power. Instantaneous power is the power at any instant of time. It is the product of the terminal voltage and current. And it's represented by the equation P equal VI. We've also seen alternative forms of the equation. The instantaneous power is measured in watts when voltage is in volts and current is in amperes. Consider the black box circuit on the right. Let's assign a sinusoidal steady-state signal for voltage and current at the terminals of the circuit. As you recall, current is our reference input value. So let's shift our voltage and current to a zero reference. Our zero reference is set to time equal to 0 when current is at its positive maximum. And the shifted values are to the right of the purple arrows. We substitute the adjusted voltage and current into the instantaneous power equation, P equal VI, and then we simplify it using trigonometric identities and assigning alpha equal to omega t plus theta v minus theta I and beta equal to omega t. This allows us to expand the expression for instantaneous power to this big thing. Now, you may be wondering, why did we take a simple, straightforward expression like P equal VI and rearrange it to P equals Vm times Im divided by 2 times cosine theta v minus theta I plus Vm Im divided by 2 times cosine theta v minus theta I times cosine 2 omega t minus Vm Im divided by 2 times sine theta v minus theta I times sine 2 omega t. Well, we can, we will, and we have used P equals VI. However, this expanded expression for instantaneous power has useful information. There's information regarding instantaneous power and its relationship to the input voltage and current, and its relationship with average power and reactive power. Let's take a closer look. You will notice that there are 3 terms on the right-hand side of our expanded expression. In looking at the 3 terms, you will notice a couple things. First, the first term is a constant. It is not a function of time. And the second thing is the second and third terms are sinusoids with a frequency of 2 omega t. This frequency is twice the frequency of our input voltage and current, which was omega t. Therefore, the frequency of instantaneous power is twice the frequency of terminal voltage and current. Also note that the instantaneous power may be negative. When the power is negative, the energy stored in the inductors or capacitors is being extracted. Likewise, when power is positive, energy is being stored in the magnetic fields associated with the inductive elements or stored in the electric fields associated with the capacitive elements. All right, a second observation. You will notice that the first two terms have the same constant. We call this constant the average power, which is also called real power. It's represented by a capital P, and the units for average power are watts, or the unit is watts. Our third observation, the third term on the right-hand side is called reactive power. And the units for reactive power is bar, which is volt amp reactive. This looks really messy, having this long expanded expression for instantaneous power, but we can simplify it in terms of average power and reactive power. So instantaneous power is equal to average power plus average power times cosine 2 omega t minus reactive power times sine 2 omega t. All right, so we now have two expressions for instantaneous power. Our simple expression, P equal VI, when terminal voltage and current are known, and our expanded expression, which helps us understand how average power and reactive power relate to instantaneous power. You would use the simple expression when, as I said, voltage and current are known. You would use the expanded expression when average power and reactive power are known. So in chapter 10, we're going to be using the second expression. That's what we're interested in. The unit for instantaneous power is the watt, even though reactive power is the var and average power is the watt. Let's look more closely at average power and reactive power. You will notice that their equations are very similar. The difference being average power is cosine of theta v minus theta I, and reactive power is sine of theta v minus theta I. Both average power and reactive power can be expressed in terms of peak magnitude, which is the V sub m and the I sub m, as well as in terms of RMS voltage and current. We discussed RMS voltage and current in chapter 9, but we will be discussing RMS power in the next lecture. So I just want to mention this here. Average power is the average value of the instantaneous power over one period. In equation form, this is the integral of instantaneous power, in which integration terminates after one period. If you recall, integration of a function gives us the area under the function. Since the area of a sinusoidal function is 0 over one period, we can eliminate the second and third terms of the expanded instantaneous power expression, resulting in our given equation for average power in the first bullet. So the watermark behind the text is one period of a sinusoidal function, and you can see how the area would be 0. Reactive power is the power exchanged between the magnetic field of the inductor or the electric field of a capacitor and the source that drives it. Reactive power is never converted to non-electric power. Instead, it is continually exchanged between the circuit and the source driving the circuit. When instantaneous power is positive, energy is stored in the magnetic fields or the electric fields. When instantaneous power is negative, energy is being extracted from the magnetic fields or of the inductors or the capacitive or electric fields of the capacitors. In contrast, average power is sometimes called real power because it describes the power in a circuit that is transformed from electric to non-electric energy. Average power is considered a more important measure of power, especially for periodic currents and voltages, because it is used to quantify the needs of household appliances. It's monitored by the electric company to determine monthly bills. It ranges from a few picowatts to millions of watts. And when you buy electrical appliances or devices, you will find a power consumption or a power rating value on the stat sheet. This would be the average power or the real power. Okay. Let's take a look at the relationships among the terms P and Q of the instantaneous power expression by examining the power in circuits that are 1, purely resistive, 2, purely inductive, or 3, purely capacitive. Using the figure below of a black box circuit, if the circuit between the terminals is purely resistive, the instantaneous power for a resistor is called instantaneous real power, which means that the voltage and current are in phase. So theta sub B is equal to theta sub I. And by definition, the average power, which is a capital P, is the average of the instantaneous power, which is the lowercase p, over one period. For a purely resistive circuit, average power is equal to 1. Instantaneous power can never be negative, and the equation for instantaneous power is reduced to the first two terms, capital P plus capital P cosine 2 omega t, or average power plus average power times cosine 2 omega t. If the circuit between the terminals of the figure below is purely inductive, current lags the voltage by 90 degrees. So theta sub I is equal to theta sub B minus 90 degrees. But we rewrite this, we like to write it as theta sub B minus theta sub I is equal to plus 90 degrees. If the circuit between the terminals of the figure below is purely capacitive, the current leads the voltage by 90 degrees, and theta sub B minus theta sub I is equal to minus 90 degrees. For both purely inductive and purely capacitive circuits, average power is 0. Since energy is not transformed from electric to non-electric. Rather, the power is continually exchanged between the source driving the circuit and the electric field associated with the capacitor plates or the magnetic field associated with the inductor elements. So our equation for instantaneous power is reduced to minus Q, which is reactive power, times sine 2 omega t. Okay, now that we have a few of the equations down, let's work on some example problems that demonstrate the concepts just learned. Our first problem can be viewed by clicking on the link to the video. Our second problem can be viewed by clicking on the link to the video. Let's review the concepts presented in this lecture. We introduced the concepts of instantaneous power, average power, which is also called real power, and reactive power. We defined the equations for each of the three concepts. And we solved example problems which related the power concepts and how to calculate them in a given circuit. And that concludes this lecture.